Hey, you're the space class. Michael here. What is time? In our everyday lives, we decipher time as hours, minutes, and seconds. And time seems to be moving at the same rate forward for everyone, right? Wrong. This is because of something called time dilation. Time dilation is the difference between a lapse time of two events measured by observers either moving relative to each other or differently situated from a gravitational mass or masses. An astronaut orbiting Earth in the ISS at 7,000 kilometers per second experiences this time dilation. For every day an astronaut is aboard the ISS, they age approximately several microseconds less than you or I do on Earth. Sergei Krikalev has spent approximately 2.2 years orbiting Earth at these high speeds. This makes him 0.02 seconds younger relative to the people on Earth. Now that might not seem like much, but when we increase the speeds close to the speed of light, things start to get a little weird. Using this equation, we can calculate time dilation at higher speeds. In the twins paradox, one of the twins is put on a rocket traveling at 99.9% the speed of light for 2.2 years, and the other one stays here on Earth. When we plug these numbers into the equation, the effects of time dilation are shown clearly. When the first twin returns from his 2.2-year journey, his twin will be 53 years older than him. Traveling that fast is very implausible, but with the advancement of technology, we could be traveling at near speeds of light in close to 1,000 years. Then, time dilation will come into effect. Now that you know what time dilation is, you're probably wondering how it actually works. Well, to understand how it works, we first need to understand c, the speed of light. Light speed is fast, really fast. So fast that it can travel all the way around Earth in 1 second. 7 times. Only massless objects can accelerate to the speed of light. Objects with mass require energy to accelerate, and to get to the speed of light, you would need an infinite amount of energy. Another weird thing about light speed is that it's constant. No matter how fast I go, the speed of light will always be c, 3 times 10 to the 8 meters per second. A person, let's call him Joe, is turning on a flashlight going half the speed of light. We are stationary relative to Joe and are turning on an identical flashlight at the exact same time he does. The light coming out of both flashlights will be calculated as c. The fact that Joe is moving does not affect how fast light comes out of his flashlight because the speed of light is constant. Now, if we go 1 second into the future, light has moved 1 light second relative to us. Joe has moved half a light second relative to us because he is moving at half the speed of light. Our clocks say 1 second has gone by because light has moved 1 light second. But Joe's clock says 0.5 seconds have gone by because he sees that the light has only traveled half a light second. Now, if we move 2 seconds into the future, we see that light has moved 2 light seconds. And from Joe's perspective, he sees that light has only moved 1 light second. Therefore, he counts only 1 second has gone by when we count that 2 seconds have gone by. Therefore, time dilation. Joe's time moves slower relative to us to keep the speed of light constant. If you couldn't wrap your mind around that, here's another way to explain it, with the photon clock. A photon is placed between 2 mirrors. Every time the photon hits the bottom mirror, let's say 1 second goes by. Now, if we take an identical clock and move it at half the speed of light, you can see that the photon must travel a further distance to reach the bottom mirror. In result of this, time moves slower for the moving clock than it does for the stationary clock. If you're really trying to get to the future fast, traveling at high speeds might take a little too long. The effects are so minimal unless you're traveling really close to the speed of light. Well, luckily for you, there's a faster way to get to the future: gravity. Gravitational time dilation works similar to relative motion time dilation, except this time you don't have to move the speed of light for years. Gravitational time dilation is caused by the curvature of space near high mass objects. Using the photon clock analogy, we could show this again. In a weak gravitational field, the light has to travel from point A to point B in a straight line. Now in a high gravitational field using the same clock, light travels from point A to point B following the curvature of space, therefore making the light travel a further distance and causing the clock to run slower. Here's an example to explain how effective this could be. First, we need a supermassive black hole. Let's use Sagittarius A, the one at the center of the Milky Way. Its mass is 4 million times that of the solar system, and its event horizon is approximately 17.6 million kilometers. This is implausible, but if we park our spaceship just outside of the black hole for 3 months, using this equation, we can calculate that 1,037 years will pass on Earth in the time that we're there. Now that's a quick jump to the future. Well, it looks like we're running short on time. If only there was a way we could slow it down. Oh wait, Thanks for watching.